All right, so let's get started. Uh, Today we're going to be talking about encryption, and we have these kind of 3 lectures. I might do these in 2. I might make a small schedule adjustment here. But we're going to talk about encryption and how we can keep ourselves protected and private on the internet through encryption. What I want to talk about before we get into that is the project. I just want to remind everyone today is the last day to submit your project checkpoint if you want to get credit for using up your next project checkpoint before the end. I changed this to 2.5 weeks, but it's 2.5 weeks before the end of the project. This last checkpoint is effectively the deadline. This is when the project actually gets graded. So hopefully everybody is aware of that. And then the project video, this is effectively your final exam. So I have it due at the end of the final exam time listed on the hub. So that's where that deadline came from, May 14th at 11 a.m. Just in case anybody's wondering where that deadline comes from. And of course, homework 5 coming up. I'm sure you're all very, very aware of that. I would imagine, unless you have it done already. So during today's lecture, if there are questions about the project checkpoint and homework 5, I wouldn't mind taking a few minutes, addressing chat and answering those questions. By default, I'm going to go through these slides. I'm going to talk about encryption. So no questions right now about project and homework. Let's talk about encryption. This is something that, I don't ask you to do on the homework or unfortunately the project either. But I do want to go through. I want to demo it. I'll go through the process in the next week. I'll go through the process of I don't know exactly what I want to do yet, but I might just start from scratch, build a project using a framework, deploy it on the internet, get HTTPS involved, get our encryption, our certs, and everything, and show you the whole process of building and deploying an app. I think that's what I want to do next week. Unless somebody has something else they really want to see, that's by default what I want to go through. The only question is, I don't know if I'm going to start the project from scratch or just pull up an existing one, explain the code base, and then go through the deployment process. If you had an issue with Chrome on homework 5 where it cuts off an HTTP request with no reason, maybe they're post requests, so you have to do buffering. If you're not buffering, then yes, that happens all the time. You have to read the headers, read the content length, buffer until you read the content length, or else you will get that. They'll cut off. The browser is well within its right to do that, to just send the headers and then send the body afterwards, or the headers and some of the body and then the rest of the body. We've went over this 23 bears. We've done this a lot. That was homework 3? We're way past that. You should be buffering. You shouldn't never have deleted your buffering code if that's what happens. If that is there that you're seeing. But that's the most common way to see that. Would we be able to ask more questions about the project during the next few weeks? Yes. So the next few weeks, and we have plenty of time to cover this encryption. If we don't even talk about encryption today, I'm fine with that. We have plenty of time. It's just one topic where I really want to talk about it because it's something you should all be exposed to, especially after taking a web apps course. But we're past the homeworks. So last Friday was the last day of homework content, and we actually turned that into a project day, like half a project day. The rest of this last section of the course, these last 3 weeks, just titled Web Apps, this is meant to be helping you with your project. So the entirety of these 3 weeks is helping you with the project. And since the projects are, you get to pick whatever you want, you're all doing different things. I am going to play off of chat a lot. If you're asking for specific things about the project, I'll show you those specific things. But these 3 weeks, I'm here to help you with the project. If y'all don't have any questions, my default is to go through this encryption content in HTTPS. And then I'm going to demo a web app. I'll build a web app, I'll deploy it. Review and examples in web app architecture. These lectures will blend together. I just gave them different labels just because. just kind of remind myself what I want to cover in these 2 weeks is the web app architecture and deployment. So absolutely, you can ask questions about the project. These last 3 weeks are going to be more open-ended lectures. So I'll interact with chat more, be more, be more laid back. Probably make for worse YouTube videos, to be honest, but there will be good bits in there. Especially if I get, if you ask questions about the things that your teams are struggling with, you'll get help with that. You'll get help with that. Unless it's too specific, I guess. We still have like 70% of the project done and do a checkpoint. For checkpoint, can we? Oh, there's the question part. Yeah, absolutely. Yeah, and then finish so the idea is that you get feedback on what you've done already. So the whole point of having the 2 checkpoints is that you get feedback. I get to say, I'll tell you whether or not you're headed in the right direction. That's basically what the checkpoints are meant for. So if you're way off track and you're doing something completely off of what you're supposed to be doing, the checkpoint is my opportunity and your opportunity to get feedback and my opportunity to give you that feedback and say, whoa, what are you doing here? This is not what the project is supposed to be. You got to be doing this, and this, not that, and that. So that's what the idea of the checkpoints are. And if it's not too egregious, it's still, okay, this part right here, you got to change this a little bit. Most of checkpoint 1 was me saying, where the hell are your reports? You have to do reports. What are you doing? That was my feedback for most teams. But yeah, absolutely. The checkpoint isn't meant to be a completed project. It's meant to be getting feedback on what you did complete. And then I mentioned that if you do have the project done at the checkpoint, then you can get a grade. I can say, my feedback is your project's done and you have 100. Congratulations, you're done with the project. Yeah, but not if you have 70% done on the final checkpoint. I mean, you'll just get a grade of roughly 70%. Like that'll be your final grade. This is the only one where I will assign a grade to every single project. You'll get your final grade. I have the buffering functionality from homework 3 and it just slices up the requests. Oh, so yeah, if you do have buffering but the buffering slices up the request, that's too specific of a question for lecture, unfortunately. If you want to come to office hours tonight, that'll help you out. Yeah, exactly. You can go to Starbucks and sniff packets. Is it illegal to packet sniff? I'm pretty sure it's not, right? A lot of times it'll be against terms of services. I don't believe there's an actual law about it. Like if 2 people are talking next to you and you eavesdrop on them, I mean, it's not illegal. People won't like it, but I don't think it's really illegal. Like Starbucks, when you log into their Wi-Fi, they probably have, when you click I agree, they probably have something in there that says, I'm not going to mess around with other people's data. So you're probably breaking their terms of service, and you're in trouble with Starbucks. You're not in trouble with the government, though. I don't believe. I could be wrong. I don't know 100%, but I believe that. And let's be honest, who's going to catch you? Imagine reading the terms of service. All right, so the problem here is that when we use HTTP like we have all semester, everyone can see, anyone with access to your packets, your IP packets, can see exactly what you're doing online. They can read all of your traffic to and from websites. Absolutely everything, and this includes your passwords, which I want to talk about a little bit. We talked about it briefly last week. I want to revisit that and do a thought experiment there. So who are we talking about? Your ISP, UBIT when you're on campus, the Tier 1 networks, the people that ISPs pay for internet access. These ones shouldn't scare you too much. We have a reasonable trust of these organizations, at least to a degree. At least to the degree that we don't believe that they would put their reputation on the line, But the scary one is everyone within your Wi-Fi range. Everyone in your Wi-Fi range, within range of your device, of Wi-Fi range, can read what you're doing on the internet. So they can sniff packets. There's software called Wireshark or TCP dump. I haven't really heard of that, but if that does the same thing. So the problem here is that Wi-Fi is not a targeted beam of information. When you're connected to an access point, you don't have like a laser from your laptop to that access point that communicates information to it. Instead, you're broadcasting information in all directions, and then the access point just knows, oh, hey, that information is made for me. But you're blasting it in all directions, so everybody within range of that signal and has a Wi-Fi card, everybody's machine is getting that information, and then there's software in your machine which says, oh, this information is not made for me, so I'm going to ignore it, I'm going to throw it out because it's not made for me. It's made for somebody else. Well, if you download software that says, give me everything that's hitting my Wi-Fi card, everything that's hitting my Wi-Fi, everything that's hitting my antenna, I want to look at what that is, well, you can do that. Like, they're literally blasting it in your face all the time. You can just read that information. So anybody in your Wi-Fi range can see what you're doing. You just have to download some special software, or I don't know, write your own. Could you? Well, you certainly can, but how hard would that be? Probably pretty hard. You'd have to link into your OS, I believe. I don't know. I don't want to think about it. But anyway, this includes your passwords. Why does this include your passwords? That's a thought experiment I want to have right now. Why does this have to include your passwords? Not necessarily have to. You know what? I will go that far. It doesn't necessarily have to. This has to include your passwords. Your passwords are sent in plain text over HTTP. At least effectively. Passwords are sent through HTTP posts. Let me get a little more specific with this question. We talked about hashing and salting of passwords, and once you salt and hash a password, nobody can read that password. Why don't we do that before we send it in an HTTP post request? You did make a simple packet sniffing tool? That's neat. Where we use SniffX. Is SniffX a library then? Anybody have... I did this earlier, so apologies if you've already seen this. I think it's still neat. I like it every time I do it. But does anybody have a website where you have to log in? That's my only requirement. It has to have a login. A method of logging in. I don't like how many ads are on that speed dial page. SFX was a library for C, from what I remember. Oh, that's cool. AutoLab. It's not as fun when it's AutoLab, but yeah, I'll do AutoLab. If somebody has a... I'll have to log out first. Oh, thank goodness those are mine. I'm like, oh my god, I just leaked grades. Thank goodness those are mine. Alright, so let me log out. AutoLab's just shibboleth, isn't it? I know that, but... So shibboleth.buffalo.edu. I'm going to go to the network tab and log in. I'm going to look at that request that I sent. Let me switch this. I'm going to look at that request that I just sent, my login request. It's a post request. It is HTTPS, which will be important. If I look at the payload here, I have a URL encoded. Let me view source because we know how to read this. It's literally what I typed in for my password. Plain text, that's what's being sent over the internet. Jory, you did this last time, didn't you, too? Didn't we already do that site? Can we get a different one? How about a bank? Anybody want to shout out a bank? Because banks, you would expect banks to have the most security possible. Whatever security technology is available, the bank should have implemented. Right? We did already do Viz. That was the site we did last time, right? Is BOFA a bank? What's that short for? Bank of America. If you're trying to set me up with Bank of America, it's not going to work. Inspect element. Oh, I wasn't on the network tab. Oh, we still got it. Look at all that crap. Plain text. Let's do one more. We'll do chess.com. Log in. Post request to login check. Password, plain text. 3 for 3. Plain text. All of them. In viz.com, we're 4 for 4 because we did that one last time. Feel free to go through any sites you want. You're going to see the same thing. There's only one. The reason why somebody suggested Bank of America. You want to see... This is actually a really interesting web app thing, so it's worth showing. If I refresh this page, I go to login, continue to sign in. And I have to find where that request was. Sign on. Where did that go? Sign on right here. Definitely not the index.com. So I want to look at what's going to be right below this. Goodness, this is terrible. Validate ID, sign in. So it's this request right here. This should be it's an options, a get, a post. Oh my goodness. And the password is actually hashed here. This is the only one I've been able to find. I believe that's why Bubber Ducky suggested that, because they knew it was going to try to set me up. So we verified that Bank of America does send passwords in plain text. And then I just refreshed the screen and did it again, and it's not plain text anymore. This is because I resized this. If I resize this back, I'm not going to have that issue anymore. Oh, I will have that issue. So the problem is what they're doing is notice how this is a different login screen. What they're doing is reading the size of the screen, and if the size of the screen is too small, actually get the mobile version of the site. And their mobile version of the site does, I believe it's an MD5 hash and then base 64 encoded of the password, which doesn't add any security, but for some reason they're doing that only on the mobile version. I would like to know from their devs why they're doing that. But if you get the desktop version, they're not doing that. It's plain text passwords. So it depends on the size of the screen, which was driving me nuts. When I first found this out, I was getting that behavior, and then chat was testing it too, and they were like, I don't get that behavior. It literally depends on the size, not even of just the screen, not even of the window, but of the viewing area of the site, which is common. You're going to get a different experience based on the size that you have. I even do that on web apps, on the course website. Like if you collapse this, I have these blank areas on the sides, but once you get small enough, those areas go away. Now I fill up the entire screen, and it has different layers as it goes. So that's a common thing, but they completely swap out their front end. They go to a larger extreme, completely swap out their front end. And you notice the first time where I resized and refreshed, it actually asked, because I might have to clear cookies. But it actually asked if I wanted to download the mobile version of the site. Oh my goodness. Spend too much time on this, ain't I? Get me out of this. Reload. And this is what happens when they're strictly... How did I get so many more cookies after that? And why is it not asking me again? Y'all saw it, right? I'm not going crazy, am I? It asked me, do you want to download the mobile app? Because they saw my screen size and just assumed I was on mobile. So some, if I may say, pretty shitty design on their end. But anyway, the thought experiment. When they are hashing that password, first of all, why doesn't everybody hash the password before being sent? And two, why am I so confident that hashing the password does not add security when they are hashing it in the mobile version of Bank of America, which is the only site, I've done this quite a few times in quite a few lectures. It's the only site I've ever found that is not sending plain text passwords. So why? Yeah, I'm sure that I would imagine they have two different teams working on that, and then they have a switch between the two apps. And that's what I'm getting at. There's something really bad going on there, unless there is some really nuanced thing, like maybe, I don't know, maybe that's just the way you do it, and there's something I don't know about. I'm open to that opportunity. But yeah, if there's two teams that don't communicate, or maybe they do communicate, and this is a common argument in Bank of America and the dev team, they're like, no, you have to hash that password before you send it. And the desktop team is like, dude, bro, I took 312. That doesn't make sense. You just don't do that. And the mobile team didn't take 312, and they're like, no, we're hashing everything. Kind of curious if that's an actual vulnerability. Like if you could actually break things. If the screen is smaller than... And they both have the same security. I'm saying that hashing doesn't add security, as long as they're hashing again on the server side. Assuming they're not only hashing client side. If they're only hashing client side, they are it's just horrible. Exactly. It's encrypted, and so that's what we're getting at. that that we're going to encrypt everything, so nobody can read those passwords. Oh, these aren't even. I updated these slides, and this isn't the updated version. This isn't the outline. This isn't the overview. I swear, I just updated the slides. But why not hashing? Like, wouldn't that just be another layer of security? So right now, the only layer of security protecting your passwords is that little S on HTTPS. We slap an S on there, we call it secure, and then we're good. But why not have 2 layers of security? Why not also hash? That's why, so don't panic that your passwords are being sent in plain text. They're encrypted, so we're good. And then the rest of these slides, we want to talk about encryption and how that actually protects us. Yeah, Dorian, if you find out what's going on there, I would like to know. I'm genuinely curious why they do that. Because they might have a very good reason. They might have a good reason to do that. Maybe they had an intern code it. Don't make that mistake if you're one of those interns. So that to send the salt is a way to get the passwords. All right, so if the client was generating the salt, they would have to send the salt over the network too. And they'd have to store that salt and then send the salt each time they submit their password, which would be kind of awkward. It wouldn't really add security to it. You want the server to control those salts. So the reason this doesn't add any security is, so say I hash and then I send the password. That means somewhere in the JavaScript there has to be a hashing algorithm that's going to do the hashing and then send the password. So on the server side, what the server is expecting then is no longer your password. The server is expecting a hash of your password. So, and the server doesn't care that the hash of that password came from your actual password. It just needs to know, I need to see the same hash, the same sequence of characters that you sent me when you registered. If you send me that same sequence, I'm going to add the salt, I'm going to hash. It's going to match what's in the database, and then I'm going to authenticate you. So from the server's perspective, it has to get a hash of your password. So if the server needs to get a hash of your password to authenticate you, I don't need to know what your password is anymore if I'm the attacker. I don't need to know what your password is anymore. I just need to pull that hash out of the air. That hash that I showed you that Bank of America is sending, that hash, base64 encoded hash, that's what you're going to have to send to the server to authenticate. You no longer have to know the user's password. You have to know the hash of their password, which is what's being sent over the air. So you grab that hash. If it's not encrypted, you grab the hash. And then when I want to log in as that person in Bank of America, I don't type their password into the box. I don't paste that hash into the box. No. I go into the JavaScript. Actually, I probably would paste the hash into the box. I go into the JavaScript. I go into where it's hashing. I delete that code. And then I paste the hash into the box with their username. Send that to the server. The server's still getting the hash that it expects. And I'm logged in as you, without ever having to know your password. So whatever is sent over the wire, whatever's sent over the internet to the server, that effectively is your password. It doesn't matter if it's some hash of something that's easier for you to remember. That effectively is your password. So who cares about what you actually typed into the box? I just need to know what was sent over the network, and I'm going to send that over the network. And if I can't find the JavaScript or whatever, I'm just going to manually send the post request. I'm just going to go into my console, type some Ajax, send the post request to log in. Done deal. Or even write my own HTML form if that's what I got to do. It's not that big of a deal. You've done that on multiple homework assignments. You're all capable of doing that. Write your own form with the correct path that you found from looking at the browser console and manually send your own post request. It's the worst. When you take the last sip and don't realize it, you go for another one. It's gone. So there's no reason to hash passwords because the hash of your password is effectively your password. And if an attacker can steal that hash, they don't have to steal your password anymore. So it doesn't add any security. As long as the attacker can send whatever's being sent over the internet, send that to the server. That's what the server expects. Authenticated, done. So the only line of security we can use, the only effective line of security available to us to protect your password is the little S on HTTP. We're going to slap an S. We're going to actually use it. It's not secure HTTP or HTTP secure, though I refer to it as that sometimes. But it's HTTP over TLS, transport layer security. This is a layer on the network stack that goes in between TCP and HTTP. So when we use HTTPS, everything that you've coded, everything you do with HTTP is identical. You reuse all of that entire thing. But when you connect, instead of just opening up a TCP socket and communicating directly over the TCP socket, you're going to add a layer right in front of the TCP socket that encrypts all of the traffic that you send to the socket and then sends it over TCP. So now we have our HTTP request, we encrypt it with TLS, and then send it over the TCP socket. So it's completely doesn't interfere with any of our code for our server. You can use an HTTP server and just slap the S on top of it. No big deal. You don't have to change a single thing about what you do as a developer. When you're developing a web app for HTTPS, effectively zero changes. Nothing changes in what you do. But when you go to deploy the app on a live server, you have to make sure you have this TLS layer. And then we call it HTTPS. We use port 443 instead of 80, and we're secure. It's part of why I scrapped the homework where I had to add this S, and not even doing it for the project. I might next semester. I might add that back in. But as a web app developer, it just doesn't really pertain to your job that much. DevOps, if you're going to get into DevOps where you're concerned with the deployment, which we do with the project, maybe I should add it, but it's a lot of, I don't know. I'm just going to explain what it is. So what is encryption? The idea of this is that we want to send a message to somebody else with only the intended recipient being able to read that message. So we want to send some plain text message, and instead of sending the plain text itself, we're going to encrypt it to generate a ciphertext, send that ciphertext over the internet. That ciphertext is structured in such a way that nobody can understand what it is. It's just a jumbled mess of characters. When the recipient receives the ciphertext, they're going to be able to read that as plain text, but nobody else can. This is the goal. This is what we want to achieve. And that's what we get with encryption. So visually, we have some message we want to send to somebody. We encrypt the message. Sending it over the internet just looks like a jumbled mess. Anybody reading this, anybody eavesdropping on this packet, on this information, this message, they can't read this, they can't decode it. But once the recipient reads it, they can decrypt it and convert it back into the original message that I sent. So to do this, we're going to see public key encryption, specifically RSA, which is one way of being able to do this, to be able to send messages back and forth. This is a public key encryption system, meaning that you have two encryption keys to be able to work with messages. One, a private key, which as the name implies is always kept private. And then the other, a public key, which as the name implies, can be shared with anybody. Everybody on the planet is allowed to access your public key and use that key. When somebody wants to send you a message, they take your public key and encrypt the message with your public key. And when you receive the message, you decrypt it with your private key. So everybody can encrypt messages meant for you. And if you're the only one who has access to your private key, you're the only one who can decrypt those messages that they sent. So there's a problem here. The keys are inherently related. They're mathematically related, as we'll see in a second. So we need a few more properties here. somebody with the public key should not be able to generate your private key. Now, they're mathematically linked, so this is possible, given a public key, to generate the private key. And it is possible to take a ciphertext and a public key and generate the plain text message. It is possible. So these are things that we have to be aware of, and any good crypto system needs to have some sort of protection against these types of attacks and these things. That's where RSA is going to come in. This is one crypto system, public key crypto system, which has these properties, we hope. Which is always the underlying kind of scary part of encryption, is it's just the best we can do, and we think it's cool. But it might not be. So live in fear always. So what we get with RSA is a way to generate the public-private key pair that are linked. We can encrypt with the public key and decrypt with the private key. And this is how we do that. One of the beautiful things about RSA is it's actually kind of simple. Like it's less complicated than it could be. You know, it still takes a little bit to read through all this. I'll go through it right now, but as opposed to, say, SHA-256, where we saw this big network of bitwise operations, and there were multiple passes through that thing. RSA, not so much. We got a very clean, elegant way to generate these keys in this formula. This is the entire method to generate keys. If you took 199 with me, you know that I have 199 students go through this math and generate public and private keys using RSA. Like, it's not crazy. Yeah, this is my 199 slides. They're a little modified. Like, there are some things I do in 199 that isn't, like, you don't need in a 300 level. Like, I cut out a lot of the simpler slides. But some of these slides are cut and paste from 199. There's no reason to recreate this slide. This doesn't change based on the course I'm teaching. So the whole key generation algorithm, think up two primes, P and Q, ideally very large primes. Multiply them together to generate N. Get the least common multiple of P minus 1, Q minus 1, and call that lambda. Choose some E that has a greatest common denominator between E and lambda of N, where E, let me reword this. Choose some E less than lambda, such that E and lambda are co-prime, meaning they don't share any common factors. Compute D, which is the inverse of E mod lambda, and that's it. You're done. E and N are now your public key. You give those to anybody who wants your public key. You say, here's my E and N. That's your public key. D is your private key. You keep that private, always, always, always. And then P, Q, and lambda, you throw those away. We're done with those. We don't need those anymore. That's what RSA, that's all of RSA, key generation anyway. To encrypt and decrypt, we take a message we want to send, raise it to the power of E mod N, and that generates our ciphertext. If we have our ciphertext, we raise it to D, our private key, mod N, and we receive M back. The way the math all shakes out, if we have M to the E times D, so we raise M to the E and M to the D, mod N, we're going to get back to M. So that's the property we get when we generate the keys like this. And since multiplication is commutative, we can actually do this in reverse. So I say encrypt with the public key and then decrypt with the private key. But we can actually do this the other way around. We can encrypt with the private key and then decrypt with the public key. Now, this doesn't give us any privacy. If I encrypt something with my private key and then send it out to the world, since everybody's allowed to have my public key, every single person can read that message. There's no privacy at all. Everybody can read that message. But what they get is an effective guarantee that I'm the author of that I wrote that message. Because the only way that public key could decrypt that message properly is if it was encrypted with the private key. And if you believe that I kept my private key safe and private, then you know that I'm the author of that message. And this is what we call a digital signature. If you hear digital signatures, this is effectively, they might be using different schemas. They might not be using RSA, though RSA is still very common. But they are signing it with their private key and then sending it out to the world so everybody can verify that I was that author. That message hasn't been tampered with by some third party. So, man, I swear I changed these slides. This is going to be saying, are you sure you want to push? No, it says push successful. You know what? Maybe I didn't refresh the page. But what about a brute force attack? We saw brute force attacks on hashes. Why can't we do a brute force attack here? So don't we still have this problem of if everybody has the public key and they intercept a ciphertext that's being sent to you, why don't they take that public key and just try to encrypt every possible message that they guess and just keep guessing and encrypting until the cryptotext matches the cryptotext that they're attacking? Why don't they just do this same exact attack that we did with hashing, except they have this public key that enables this attack instead? And they certainly can. They can do this attack. So, but fortunately, we have a very, very powerful protection against this called padding algorithms. So instead of just sending the information that we're trying to send, instead of just encrypting that, what we instead do is add a whole bunch of random garbage to the message that we're sending and then encrypt it and then send it. Now, when a brute force attacker tries to attack that cryptotext, they don't only have to guess our message, which has some unknown entropy. Like if for example, somebody asks you a yes or no question, you have 1 bit of entropy in the message that you're sending. That can be cracked in no time. 1 bit of entropy. But you add, say, 1,000 bits of random garbage to the end. Well, now you have 1,001 bits of entropy, and the attacker has to guess all of that entropy. They have to guess that entire padding, all that random garbage, to be able to match the cryptotext. They have to guess every single bit of added information that you added to that. So you have ridiculous amounts of entropy once you use a padding algorithm. And then when you're sending this message to somebody, what do? There's all this random crap on the message. What do? How do they handle this? Well, they decrypt. You have some note in there that says, here's where the padding starts. And you ignore everything after that note. Or some special character, or however they want to encode it for that algorithm. They just say, here's where the padding starts. You delete all that stuff, and then you get your answer yes or no with 1 bit of entropy, and you just ignore all the padding. So the padding is very important to the attacker because they have to guess that padding. But for normal use, you just decrypt and throw away the padding. No big deal. You don't even think about it. Unlike salting, this does add entropy. The padding is never in plain text. It's encrypted as part of the message. So this does add entropy. And this does get us ridiculous amounts of security with encryption. Like, encryption is extremely strong. Where hashing, we had all kinds of attacks that we were talking about. With encryption, even if you're sending 1 bit of information, using padding algorithms, we can still be safe, we can still be secure, and have these attackers not be able to attack that cryptotext. And if they start getting close, hell, we're just going to add more padding. We have an infinite amount of entropy that we can add just by adding more and more padding. It's no big deal to add more padding. So if they start getting closer, they start getting powerful algorithms, we slap some more padding on there. Or powerful machines, I should say. Powerful algorithms might break this. So speaking of powerful algorithms, looking at this math, it seems like this is pretty easy to break. If you have N and E as your public key, meaning everybody gets those 2 pieces of information, what's stopping an attacker from taking N, factoring it, finding P and Q, And once they have P, Q, and E, because E was chosen, just has to have these properties. So E was chosen. Everything else is computed. There's only one choice for each of them. Once they factor N, they have P and Q. They can, they already have N. They can compute lambda. They already have E. They can compute D. What's stopping somebody from doing this? That'd be super easy. The only extra step they need to do that you didn't do when you generated your keys, the only extra step is factoring N into P and Q. Everything else is the same thing you did to generate the keys. So if that's impossible, then we just can't use RSA at all. The only extra step was factoring N. So this seems like a problem, but luckily, factoring, as it turns out, is ridiculously hard, specifically factoring the multiplication of two large primes. As it turns out, that's an extremely difficult problem. We don't have any efficient algorithms to factor. It seems like such a simple thing, factoring. I mean, that could be a one. I actually had it as a 116 question, one of the lecture questions. Factor the input, and 116 students can do that. Like, they can factor inputs, they can write code to do it. But once the numbers get very large, we can't do that efficiently. Your factoring method is probably going to just guess every single possible number, divide. If it divides evenly, that's one of the factors. So once you have to go to a very large prime to be able to factor, to be able to find the first factor, we actually don't have a good algorithm to do that. It doesn't exist. It at least doesn't exist publicly, and I believe that it doesn't exist privately either, because if somebody had that kind of power, they could, I mean, there's just a lot of stuff they can wreck if they have an efficient factoring algorithm. There is an efficient factoring algorithm for quantum computers. Once quantum computers become a thing, we won't be able to rely on factoring being hard anymore. But one, that's probably a little bit down the road, and two, we have other, this is what we call a cryptographic primitive. We have other cryptographic primitives. So a cryptographic primitive is a problem that we believe is very hard to compute. And if we can prove that breaking our encryption scheme implies breaking one of those hard problems, or efficiently solving one of those hard problems, then we're going to call that secure. Okay, great. There's another problem here, though. If somebody has a cryptotext, they have the cryptotext, they have E, they have mod N, or they have N. So all they have to do is compute the discrete log base E of C mod N. And once they compute this, which is just a logarithm, they can compute that as well. But since this is a logarithm mod N, we call it a discrete logarithm. As it turns out, that's hard too. We don't know how to compute discrete logarithms either. So we're good. Both of the ways to crack RSA are cryptographic primitives. So we're happy about this, and we're calling RSA secure. We hope. So since I set this up, I want to do this just quickly. So here's an encryption example. I'm going to encrypt meet us at the stick. I'm going to encrypt twice with the same public key. I'm going to print out the ciphertext, and I'm going to decrypt twice with the same private key. And I'm generating the key pair using RSA, which by default has a padding algorithm. I can switch it to this padding algorithm specifically. But let's run this thing. And just to verify, just to kind of visualize what's happening here, the cryptotext I hashed twice with the same message, the same plain text, same public key, ciphertext 1, ciphertext 2, and they're very, very different ciphertexts because of the padding algorithm. Yet when we decrypt, the decryption technique is going to decrypt this cryptotext, throw away the padding, and just give me the message. So I still get the same message both times. So both of these encrypted, these cryptotexts contain the same exact message, encrypted with the same exact key, but each time you encrypt, since we're using a padding algorithm, we're going to get very different results. And And by default, this library, just plain old RSA, gives us a padding algorithm. Or we can specify a very specific padding algorithm if we want to do it that way. We'll get the same results. Or not the same results, but it'll look the same to us because it's crypto text. But we encrypt multiple times very different crypto texts.